This is a video from section 4.7. Example 1 says to find the dimensions of the rectangle with perimeter 100 meters, whose area is as large as possible. So we're going to let x and y be the dimensions of the rectangle. And so when doing optimization problems, you really have two pieces of this. What are you trying to minimize, or what are you trying to maximize, and what is the constraint? And in this context, when I talk about the constraint, is the question you want to be asking is, how does x relate to y? Okay. Now, in this problem, notice the word large. So what that tells me is I'm trying to maximize the area of the rectangle. So the area A of a rectangle is given as x times y. The constraint is, how does x relate to y? But we know that the perimeter is fixed at 100 meters. So we know that 2x plus 2y is equal to 100. And if I solve for y, I get 50 minus x. But we know that x and y are positive, right? Because if x is 0, that doesn't make a whole lot of sense, because then you're talking about a degenerate rectangle. And it doesn't make any sense for x to be negative either, right? So we're going to look at x and y being positive, but notice that if y is positive and y is 50 minus x, then 50 minus x is positive. But if I solve for x, I get x is less than 50. So what that tells me is that x is greater than 0 and less than 50. So it's really good to look at those restrictions, because if I'm talking about a closed interval from the extreme value theorem, I would have to evaluate the endpoints. In this context, we don't, because it's an open interval. Okay. Now, a of x, so I'm restricting the area to a function of one variable by replacing y with 50 minus x. So a of x is x times 50 minus x. And I'm going to distribute the x in. And so a of x is 50x minus x squared. Take the derivative to get 50 minus 2x. So I'm going to set the derivative equal to 0 and solve for x. And what I'm doing here is finding the critical number. And so in this context, x is 25. Now, I'm going to apply the second derivative test. And so I start with the derivative, which is a prime of x is 50 minus 2x. I'm going to take the second derivative, which is negative 2, and I'm going to plug the critical number into the second derivative. And when I do, I get a double prime of 25 is equal to negative 2, which is less than 0. And that function is concave down. Okay? And so that tells me that the maximum, well, I think concave down, and so that tells me there's a max. And since a prime of 25 is 0 and a double prime of 25 is less than 0, then the area is a maximum at x equal 25. And so the dimensions of the rectangle are 25 meters by 25 meters. And so that's example 1. Example 2, find the point on the line y equals 2x plus 3 that is closest to the point 0, 0. And so what we're going to do is we're going to let xy be a point on the line. If we minimize the square of the distance, and I'm going to draw a picture of this, by the way. If we minimize the square of the distance from the point xy to 0, 0, we will in fact have minimized the distance. And so notice here, I draw a picture of the line y equals 2x plus 3. So this is the line in blue. Okay? So I'm tracing over it. And here's a point xy. Let's just suppose, for sake of argument, is there. So I'm trying to find a point on the line so that the distance from the origin to that point is as small as can be. Minimize, okay? So we want to minimize s, which is the square of the distance, which is the difference in the x value squared plus the difference in the y value squared. So in other words, s is going to be equal to x minus 0 squared plus y minus 0 squared. The constraint is how x relates to y. So you notice in each of these problems, I have what I'm trying to minimize or what I'm trying to maximize, and I have a constraint. My constraint is y equals 2x plus 3. So I come over here, and I'm going to replace y with 2x plus 3. And that's exactly what I did. And I just have one correction here. That's a plus. So s of x is x squared plus 2x plus 3 squared. I take the derivative, I get 2x plus, applying the chain rule, I get 2 times 2x plus 3 times 2. X and y can be any real number, by the way. So I don't have any restrictions on x and y. So s prime of x is 10x plus 12. And so here, I'm going to set the derivative equal to 0. And so that says 10x plus 12 is equal to 0. And so x is going to equal negative 6/5. And then start with the derivative. I'm going to take the second derivative. I get 10. And I'm going to plug negative 6/5 into the second derivative, and it's still 10, which is positive. And that's telling me the function is concave up, like so. And that tells me there's a minimum there. And so since s prime of negative 6/5 is equal to 0, and s double prime of negative 6/5 is greater than 0, then s has a minimum at x equal negative 6/5. And so if x equals negative 6/5, then y is equal to 2 times negative 6/5 plus 3. And I got 3/5 when I added that up. So the point, excuse me. So let me write it this way. The point on the graph of y equals 2x plus 3 that is closest to 0, 0 is negative 6/5, 3/5. And that's how you do example 2. Suppose we look at example 3. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. So what we're going to do is we're going to let x and y be the dimensions of the box. And so we want x and y to be positive. It doesn't make any sense for the dimensions of a box to be negative. Okay, so that's the restrictions on x and y. So to minimize the amount of material you use, we're going to minimize surface area. So you notice I'm not counting the top of the box for the area, right? Because this is side X and this is side X, but there's no material on the top, only on the bottom. So that's where this x squared comes in. And the area of one of the sides is x times y, but I have to multiply by 4 because there's 4 sides, 4 lateral sides. Now the constraint, okay, remember that the constraint is how does x relate to y? We know the volume is fixed at 32,000 cubic centimeters. So I know that 32,000 is the area of the base times the height, or in other words, 32,000 is x squared y. So if I solve for y, I get 32,000 over x squared, and I'm going to plug that into s. And so I'm going to reduce s to a function of one variable. So s of x is equal to x squared plus 4x times 32,000 over x squared. And 4 times 32,000 is 128,000. So s of x is x squared plus 128,000 over x. So I'm going to take the derivative. The derivative of x squared is 2x. The derivative of 128,000 over x is minus 128,000 over x squared. I'm going to set the derivative equal to 0. Same game. I'm going to find those critical values, or in this case, value. So 2x minus 128,000 over x squared is equal to 0. So I just divided everything by 2, and I got x minus 64,000 over x squared equals 0. So that told me x cubed is 64,000. And then I just take the cube root of both sides, like so, right here, and I get x equal 40. Remember that x is positive, right? We can't have a negative length. Now, again, I'm going to go for the second derivative test. S prime of x is equal to 2x minus 128,000 over x squared. Take the second derivative, I get s double prime of x is 2 plus 256,000 over x cubed. If I plug 40 into the second derivative, it's positive, and so I'm thinking concave up. So notice here, concave up, and that tells me I have a minimum. And so since s prime of 40 is 0 and s double prime of 40 is positive, s has a minimum at x equal 40. And so if x is 40, then y is 20. And so the dimensions of the box are 40 centimeters by 40 centimeters by 20 centimeters. And so I'll make another video, but notice in each of these examples, I'm very aware of what my interval or my restrictions on x and y are. Okay, because in each of these problems, I'm not dealing with a closed interval. And so if I was dealing with a closed interval, then I would have to test those endpoints by the extreme value theorem. But in the context of these questions, I did not have to do that. So, okay, that'll conclude this video for section 4.7, where we worked 3 examples of optimization problems. All right, thank you.